Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily lead code problem, and the problem's name is minimum increment to make array unique. So you will be given an integer array, nums, and in one move you can pick any of the index of this particular array and increment the number present at that index in this particular array by 1. Okay, and this will you know uh, increase the number of moves to 1. So you just made one move by increasing element at any index in the particular array by 1. Okay, and you have to return the minimum number of moves that will be required so that every value in this nums array is unique. Okay, so there might be some duplicates in this given nums array, and you have one operation to make them unique, which is incrementing the number by 1. Okay, so and it is mentioned that the test cases are generated so that the answer fits in a 32-bit integer. Okay, so you need not to worry about uh, you know typecasting or something, or taking a long or something. uh, Integer data type will be sufficient to solve this particular problem. Okay, let's have a quick look at the constraints also before thinking of an approach. So according to the constraints, the length of the array and the entries in it will be of order 10 raised to power 5. Okay, so let's discuss the approaches to solve this particular problem. So the very first approach that is coming to my mind is, if let's say the given array is this, and we are required to make minimum number of moves in order to make all the entries distinct. Okay, so here, since we will be dealing with the duplicates, so it is very intuitive to think about it like this, that we are visiting them in a sorted order. So 1 1 2 2 and then 3 and then 7. Okay, so why we have sorted the array? Because when we will be visiting, okay, so we will be starting by the very first number. Okay, so let me take the code also to the board so that you will be able to understand the approach in a clear way, and it will take less time since we will be discussing two approaches for this particular problem. Okay, so let's take this code to the board and try to understand it with the help of this example. Okay, this is the code, and let's write the example again. So 321 and then it's 217. Okay, now let's sort it. 1 1 2 2 3 7. Okay, so why we have sorted it is, first of all, we will be starting from the very first number, which is this number, and we will set the expected number to be 1. Okay, so then we will arrive at this number, and we found that the expected number is equal to the current number, so we will be traversing the sorted array in left to right direction. Okay, so if the expected number is equal to the current number, then we are just fine. Then what will be the next expected number? Okay, so what you will be expecting next? So let's say you are expecting just one greater than the current number. Why is it so that we are expecting just one greater than the current number? Is because we are greedily trying to minimize the number of moves. Okay, So greedily trying to minimize number of moves. Okay, that's why we are expecting just 2. Okay, now what might be two scenarios that might happen, that the real number is either greater than 2. Okay, so the real number is either greater than or equal to 2. Okay, in that case we are fine. I will be saying that okay, it really does not matter, we are good to go because the at least the number is not repeated. Okay, so what will happen if the number is not less than, is not greater than 2? Okay, so basically equality will not be there, only greater than 2. If it is not greater than 2, it is for sure that a number on the right hand side of the current number, it will be not lesser than it, because we have already sorted the array in ascending order. Okay, so either it should be equal or it should be greater. So the chance of it being greater is already being eliminated. So if let's say it is equal uh, to the previous number, okay, which will be nothing but, okay, here pardon please, equality will be there because it is the expected number. Okay, so if it is 2 or greater than it, then we are fine. Okay, so if it is lesser than 2, it means that it will be equal to the previous number, so we are encountering a duplicate. So in this case we will be encountering a duplicate value which is lesser than 2, so it can be only 1 because we have already encountered 1 as the previous number. So here it is a duplicate. So we will find that what is the difference between the duplicate and the expected value. Okay, since we have greedily taken the expected value to be the minimum expected value possible, unique expected value to be no exact, so unique expected value, uh, so the duplicate values difference and unique expected difference will be the number of moves required to make this, minimum moves required to make this number unique. So we will add it to the moves. Okay, else if it is not the case that we are lying in this scenario that it is greater than or equal to 2, then you will say that the expected number, you will update your expected number and just increment the expected number to one more than the current number. Okay, at last in both of the scenarios. So at last you will be returning the number of moves. So again to summarize, we have just sorted the array so that we should be handling the duplicates efficiently. Then we are generating the expected number based upon the current number. Okay, and we are taking the unique expected number to be as small as possible so that they remain unique, and we are just taking one greater than the current number. And if the expected number is not, is less than the, if the current number is less than the expected number, then we will say that for sure we have encountered a duplicate, and in that case your number of moves will be incremented. Okay, and else your expected number will be just updated, and things will proceed like this. So this is one approach. So if we talk about the complexities of this approach, time complexity wise, let's say the size of the nums array is n. Okay, then its overall time complexity will be an order of n log n because of use of this sorting that we have done. Okay, and space complexity wise, you must have observed that we are not using any extra space, so it is constant. Okay, constant extra space. So these are the complexities. Now moving further and trying to optimize this approach also. So what we can do here is, as per the constraints, the each entry in the nums array is of order 10 raised to power 5. Okay, so we can definitely take a array of size 10 raised to power 5, of order 10 raised to power 5. Okay, so this much memory is allowed, basically, uh, in the programs. So we can take the space complexity around 10 raised to power 5, and we will have a trade-off between the space and the time complexities. So how it will reduce the uh, time complexity, let's discuss about that. For that, we will be using a algorithm which is called counting sort. So what basically happens in counting sort is, let's say array is given to you 1 2 3. Let's take the previous example itself, 1 1 2 2 3 7. Okay, so we will see that what is the maximum value in this array. Okay, let's say it is not in sorted form. Just we will find out what is the maximum value. So maximum value here is 7. So we will, how we will be representing these values in a frequency map is, each index in the frequency map will represent a value, and each entry in the frequency map will represent the frequency. So what I am talking about is, let's mark the indices of the frequency map. Let's say this is the frequency map. It is basically a array of size 7 plus 1, which is 8, because it was the maximum value, and since we will be using a zero based indexing, so we have used it. Okay, so 0 1 2 3 4 5 6 and then 7. Okay, so 8 size array is uh, you know declared. So these are the numbers. Indices are considered as numbers. So these were the numbers. Okay, these. So corresponding to every number, we will increment its frequency by 1. So 0 was not occurring anywhere, so its frequency was 0. Let me use another color. Its frequency was 0. One's frequency will be 2, since it is occurring twice. And similarly, 2's frequency will be 2. 3's frequency will be, I think I have used one extra 3. Yeah, so we should be deleting that. Okay, now we are fine. So 3's frequency will be 1, and then these all will be having 0 frequencies, 4 5 and 6. Okay, and then 7 will be having 1 frequency. So if you want to sort the array, let's say it was not in sorted order, let's say it was in its original order, which is 3 2 1 and 2 1 7. Okay, so let's say it is something like this: 3 2 1 2 1 7. Okay, let's say it was not in sorted order. Then from this we have formed this frequency map. Okay, so these are the frequencies, and these are the numbers represented by the indices of the frequency map, or frequency map array, you can say. So when you want to sort this one, you have to just traverse this array and find out the indices which are not, whose frequencies are not equal to 0. So let's say we found the first entry whose frequency is not equal to 0, and it was occurring twice. So we will add 1 twice. Then we will come to 2, adding 2 twice. Then 3, 3 only once. 4 5 6 will be added 0 times. So proceeding further, coming to 7. 7 will add it only once. So this will be the sorted order. So this is how counting sort works. Okay, now we will see that how we can apply this concept to bring down our time complexity, and doing a trade-off between the time and space complexities. Okay, so let me take the next implementation to the board. So this is the implementation. Just a second. I think there is some issue in color coding. Now it should be fine. Okay, so this is the implementation. So what we will be doing is, first of all, as we talked about in the standard counting sort, we will find the maximum element. Okay. So once we are having hold of maximum element, we will be making a frequency map. This time we will not be making the frequency map maximum element plus one. I will tell you why so, but we will, further down the line, uh, but we will take the size to be maximum element plus the number of entries in the nums array. Okay, because we are trying to greedily increment each duplicate's value by one. Okay, so let's say all the entries in the array are duplicate somehow. So we will be wanting that the maximum, the number that will be generated should be, the size of the frequency map should be such that the maximum number that can be generated under any given condition should not exceed the available indices in the array. Okay, so consider a situation like this, that the entries are like this: 2, 2 and 2. So this is a 3 size array. Okay, and let's say the maximum element was found to be 2, and we just took it the size up to 3. So 0, 1, 2, these will be the indices in the frequency map. Okay, fine. uh Firstly we will be adding 2. Okay, its value is added. Okay, no issues. Then this value comes out to be duplicate. We should be incrementing it at least by 1. So in order to increment it, it will become 3. So you will see that you are out of the indices. So this 3 index should have been here, but it is not there. So this will uh, not solve the problem. And even further down the line, if you move, the next entry should be, since 3 is already there, you cannot just add 1, you should be adding 1 twice. So 2 moves here, so it will become 4. So 3 and 4 entries are missing. So that is why. So the maximum element value was 2, and the size of the array was 3. So the overall size of the frequency map should have been 5. 2 plus 3 is equal to 5. So this will be a 5 size array, and since zero based indexing is there, so these will be the sufficient indices to represent everything. So that's why we have taken this value, maximum element plus nums plus size. Okay, now moving further down the line, we are just populating the frequency map as we discussed in the counting sort. Each number is represented by an index. Okay, so corresponding to each index, each number being represented by an index, we are incrementing its frequency. Okay, now moving down the line, what we are doing here is, for each number which is nothing but the index in the nums array, this frequency map, so we will be checking all these indices. Okay, so for all these indices, if let's say the current frequency of a number is greater than 1, it means it is having some duplicates. If it is 1, then you are just fine. Since it is just a unique value, we need not to worry about this. So if let's say duplicates are there for the current number, okay, duplicates are there, then what we will do, uh, first of all, the very first thing that you will do, you will separate one frequency from the number of frequencies. Let's say this was 2. Okay, so 2, what will be the number of frequencies of 2? Here it will be 3. Okay, so you came traversing this uh, array from left to right direction, and you came at this particular index 2. you found that its frequency is 3, which is definitely greater than 1. Okay, then you came to know that okay, there will be some duplicates, but the very first occurrence will be not counted in the duplicates, so that's why you decremented the frequency by 1. Okay, their frequency is being decremented because at least one occurrence, each number is allowed to occur once, and it will not be considered into duplicates. Okay, so one frequency is already consumed, you can consider it. Then what will happen next is, uh, you are having two duplicates of this number, which will be moving. Let's say what we are doing here is we are adding these duplicates to a bag. Okay, and taking them further down the number line. Okay, so while we will be taking them further down the number line, we will be moving some steps. Okay, so those steps will be nothing but, for the first two we will be moving only one step, and for the second two we will be moving two steps. Okay, so if we add the frequency to the number of moves, to the number of duplicates, this is basically a number of duplicates, then we will say that for the very next step that we will be taking, both of the entries or both of the duplicates will be in our bag. Okay, that is a different matter, that further down the line, if one of these duplicates can be consumed. Okay, so one of these duplicates will be inserted into the index 3 here. It will be inserted as value uh, 3. Okay, so it is now 1, 2's frequency is now 1, and 3's frequency is now 1. Okay, now we will see that uh, number of so we will be moving further down the line. Okay, since 3 was not having any duplicates, we are just fine. Okay, then we are just left with 1 2 in the bag. Okay, so we just walked one step, and then we are walking one step again. Okay, so then the extra 2, which is only 2 left in the bag, will be inserted here as 4. Okay, so how many steps did we take? First of all, we take steps for 4 and one step for 3. So that is why this thing will work out. Okay, and this will be the approach. Okay, so you are greedily keeping one frequency, at least one frequency of each occurrence, and taking the duplicates in a kind of a bag and adding it to the number of moves required. Okay, at each step you are doing so, and you are incrementing the number of duplicates at uh, the next number, just next number to the current number. Okay, so 3 will be having here a kind of frequency equal to 2. Okay, so one of the frequencies will be consumed here, and the next expected number in a way will be 4. Okay, so only one frequency for 3 is left, and the next expected number is 4. So 4's frequency will be set to 1, which is the one remaining, which was the one remaining 2. In a way you can say that. Okay, so 4 will be having one frequency, and once 4 is having one frequency, then we are pretty much done with it. Okay, so this is the whole approach. This is just the next expected number. Okay, if you want to relate it with the previous approach, which was this approach, we are generating the expected number. Okay, so just adding 1 to the current number and adding the duplicates frequency. Okay, increasing its frequency by the number of duplicates. Okay, that is what we are doing here. So this is the whole approach. Again, to summarize, we make a trade-off between the space and time complexities in order to reduce the time complexity. So what we are doing here is we are applying counting sort. Okay, so in counting sort, you take a frequency map kind of thing, okay, or array basically, uh, where the number of indices in the array are sufficient so that every number in the original array can be accommodated as indices, okay, and their frequencies will be the values in the frequency map, okay. So as we discussed, the numbers will be the indices and the values will be their frequencies. So this is counting sort. Oh, that is fine. Okay. So then we discussed why we have taken this size to be this maximum element plus number plus size. I poked you around with this example that if all the entries are equal, then in that case we should be wanting that maximum element plus size should be the number of available indices. Okay. So in that case, 3 and 4th indices were missing. So that's why at least 5 size was required. Okay. So then we populated the whole frequency array, frequency map, you can say. Like, okay. And then once we are done with it, what we are doing here is for every number which is having some duplicates, first of all, we are keeping its one frequency aside because we want the number of duplicates of the current number other than its single occurrence. Okay. So that's why decrementing its frequency by 1, and then we are saying that okay, the current frequency of the number will be 1 and all the duplicates will go into the next expected number, which is num plus 1. Okay. And num plus 1's frequency will be increased by the number of duplicates. Okay. So this is the number of duplicates of the current number. That is the whole approach, and the moves that will be required will be incremented by the number of duplicates each time. Okay. So that is how you will be approaching this. And if we talk about the complexities here and the space complexity, time complexity wise it will be nothing but order of, let's say the size of the nums array is n. Okay. So n plus maximum element. Okay. So this will be the time complexity, and space complexity wise it will also be the same. Okay. Because of this loop, time complexity will be this. Okay. And space complexity because of size of this frequency map. Okay. Order of n plus max element. These will be the complexities. As you can see that from n log n time complexity we have reduced it to somewhat linear time complexity by making a trade-off between space and time complex. Okay. So these will be the two approaches to solve this particular problem. If you are still having any kind of doubts or any queries in general, then you may ask them in the comment section. I hope this solution walkthrough added some value to your journey of honing your DSA skills, and I will see you in the next video. Till then, keep practicing problems, and thank you for watching.